Okay, let's move on to Chapter 5, which is the Bernoulli and energy equations. So here's wind turbine farms. The mass, energy, momentum, angular momentum balances are utilized to design a wind turbine. The Bernoulli equation is also useful in the primary design. So this is just showing you what we use the energy equations for and how Bernoulli's equations are also applicable to daily life. Here's our objectives. So we've gone over many conservation laws. And so in the thermodynamics class, the first law is that energy is never created nor destroyed. It's just merely transferred. So it's transformed or transferred from one state to another, or one type of energy to another. Maybe it be from potential to kinetic, and so forth. And so therefore, by its nature, it's a conservation law, right? And so because all of it is transferred, so we are conserving the energy, we are just using it in different capacities. Historically, conservation laws are first applied to a fixed quantity of matter caused a closed system, and that is actually what we model our entire universe off of, is the assumption that we are inside of a closed system. And then once we master that equating in a closed system, because it's easier to not have outside influence, right? Then we extend it into control volumes with flows. And within that, we use balance equations. And they conserve any quantity. And basically what we do is we take those outer influences and then we balance them using the balance equations. And so here is the conservation of mass relation for a closed system. And if you're taking this with a thermal class, you're going to see some overlap in some areas. You know, maybe in here you'll see some things and you'll think, oh, we got to that in thermo, or you'll get in thermo and you'll think, oh, we covered that in week 2 of fluids. So these are two very related classes. Anyway, the conservation of mass relation for a closed system undergoing a change is explained here. So mass relation for a system is equal to constant, or the change in system is over the change in time, which is equal to 0, right? So that's for a rate form. Here's the mass balance for the control volume in a rate form. And remember, anytime we have this dot over something, it denotes a rate. And then we have mass in and mass out. And then again, the rate of change in mass within a control volume, because D is change, as well as if you used a little triangle, and volume boundaries. Continuity equation in fluid mechanics. So this is how we take something that's very prominent in thermo and apply it in a fluid mechanism. In fluid mechanics, the conservation of mass relation written for a differential control is usually called the continuity equation. So linear momentum, you could definitely think that that's related to the flow of our fluids, right? The product of mass and the velocity of a body that is called the linear momentum, or just momentum of a body. And the momentum of a rigid body, and anytime we see rigid, we know that work is equal to 0, because boundary work, right? Because this body is not moving. So let me put a little b here. Oops. Anytime we see that. Well, my b is just not, okay. My boundary work is equal to 0 because the body is not moving, right? So the boundary is not moving. The momentum of a rigid body of mass m moving with a velocity is mv. Newton's second law, the acceleration of a body is proportional to the net force acting on it and inversely proportional to its mass. Conservation of momentum principle, the momentum of a system remains constant only when the net force acting on it is 0. And then linear momentum equation in fluid mechanics, Newton's second law is usually referred to as the linear momentum equation. So here's the conservation of energy principle, or the energy balance. The net energy transfer to or from a system during a process must be equal to the change in the energy content of the system. So it's just conserving, right? So the energy transfer to or from a system must be equal to the change in energy constant of the system. So if you have 3 going in, then your system must increase by 3. If you have 3 going out, then your system must decrease by 3. So it's just the balance, right? Easy enough. The rate of energy in less the rate of energy out is the change in the energy of the control volume over the change of time. And again, we're just adding in that rate because we're incorporating this time. And then again, total rates of energy transfer into and out of the control volume. And then we just went over what that is. In fluid mechanics, we usually limit our considerations to mechanical forms of energy only. So we're not going to get into molecular forms, right? We're looking on it on a macro scale. Let's go ahead and make that note. Macro scale. So in the laws of thermodynamics, energy is defined as a property. Also, mass is a property. It's a conserved property. It cannot be created or destroyed during a process, and that's the conservation of mass. So we have the conservation of energy, and then we also have the conservation of mass. So we cannot create it, we cannot destroy it. It's the same thing, just on a mass basis. Closed system, the mass of a system remains constant during a process. Okay, and so really quickly, if you have a system and here's your boundary, you cannot have any mass interaction, internal or external to the system, exchange, right? So if you have your system and you have your boundary, then you cannot have any mass interaction with the surroundings or leaving the system, right? So nothing coming in, nothing coming out. Control volumes, mass can cross the boundaries, and so we must keep track of the amount of mass entering and leaving the control volume. So if we have a control volume, so let's say we have a nozzle, and we have mass in and mass out, then this is our control volume, right? So mass can cross these boundaries because when we're looking at a system, remember, a system is just whatever we're looking at. That's all we're looking at. And what we are establishing as our system can either have a real or imaginary boundary. And so therefore, if we have a tube, but we're not looking at 100% of the tube, we're just looking at one area, well, that is our imaginary boundary. And so therefore, we have an inlet and an outlet, or multiple outlets, multiple inlets. It can be a complete imaginary boundary, and every portion of it is an inlet and an outlet. Then we need to keep track of the amount of mass leaving and entering the control volume and equate that. So here you can see mass is conserved even during chemical reactions. So if you have 2 of H2, 16 of O2, that's going to be 18 of H2O. So that's going to be your mass conversion. See, we took all of it. Okay? And then mass and energy can be converted into each other. E equals mc squared. And then C is the speed of light in a vacuum, and that is a constant. The mass change due to energy change is negligible, And that's how we're able to have this conservation of mass. So we have mass flow rate. It's the amount of mass flowing through a cross-sectional area per unit time, of course, because it's a rate. So anytime you see a rate, you know that you're going to take into account per unit time. So it's just the mass flowing through a cross-section at a time. The differential mass flow rate here. The point functions have exact differentials. So these, you have the cross-sectional area. And then the path functions have inexact differentials. So it's this, not this. Okay. And this is just defining those formulas for you to use. Here again is just more defining mass flow rate, volume flow rate, average velocity, taking into account those differentials, right? And then here you can see it, velocity average. The average velocity is defined as the average speed going through a cross-section. So these are equal, right? And then we have the volume flow rate is the volume of fluid flowing through a cross-section per unit time. So this is just it. Pretty easy. Okay, so the conservation of mass principle for a control volume. We talked about this. It is the mass entering the control volume at a given time less the mass leaving the control volume at a given time is the net change of mass within a control volume. And remember, I want you to think about this. If you ever get a little bit hung up on the conservation of mass, I want you to remember that, well, obviously this is a fluids class, right? But basically what we are working with, whether it be a gas or a vape or a liquid, the vast majority of time we are working with incompressible substances. I don't even know if we're going to get to any sort of compressible substance in here. I don't think so because it's fluid and those are extremely rare. But we have incompressible fluids, right? So therefore, if we have 10 in our little boundary, I'm not even going to use units right now because I don't want to muddy the water. But if we have 10 units of H2O and we have 3 forcing its way in, well, we're not going to suddenly have 13, right? We're not going to have that. We're going to have 3 exit. We have to, because our pipe's not going to get bigger. I mean, if there's enough force, it will cause the pipe to fail and break, you know, and then we won't have our boundary anymore. But our control volume's always only going to be 10, right? And so therefore, the total mass entering the control volume at a rate of time less the mass leaving the control volume rate of time is the net change, okay? So here, mass in less mass out is the change in mass. And overall, we have the conservation of mass principle, right? Mass balance is applicable to any control volume undergoing any kind of process. Here, conservation of mass principle for an ordinary bathtub, so you can see it. Mass in, and this is if it was empty. So in our last example, this had 10 in it, right? We started off saying this has 10. If 3 more comes in, we don't have 13. You know, 3 has to exit, and that shows our conservation of mass. This is showing the mass in an empty bathtub. So if we have 50 going in and 20 is being collected, well, then we have to have 30 coming out. Here's some more just velocity, rate change, differential, net flow, just more formulas. The general conservation of mass formula here, and we balance that, so we set it equal to 0. Okay. And then here we just shows the conservation of mass equation is obtained by replacing B in the Reynolds transport theorem by mass and B by 1. So this is just showing you how we get from here to here. A control surface should always be selected normal to the flow at all locations where it crosses the fluid flow to avoid complications, even though the result is the same. So this is just saying how to set it up. So it's normal to the flow. That's important. So if you have a flow, going this way, your pipe should be like this, which is how we draw them, right? That's how we draw our things. Don't draw your flows like this. Even though the result's the same, it just makes it messy, and it's important to be consistent. So more moving or deforming control volumes. This is a very long paragraph that I'm not going to read, but it's when we start looking at injection of medication through a needle or syringe by force, involve deforming the control volumes. It's just talking about where it is, why it's important. Mass balance for steady flow processes. So if we have a steady flow, which means it's unchanging, right? Then the mass in the control volume is constant, right? The total amount of mass contained within a control volume does not change with time. So we have mass rate going in, mass rate going in, and the mass rate going out. Oops. It's just these two added together, right? Mass balance, and we have that conservation of mass as well. So for steady flow processes, we are interested in the amount of mass flowing per unit time, and that's the mass flow rate. And we see those in versus out, the sums of all of those, if you have multiples. And then this is single stream. Okay, and then here, which we will work at, many engineering devices such as nozzles, diffusers, turbines, compressors, and pumps involve a single stream only. And we start off using those because they're easier to solve. And again, you see that conservation here, conservation of mass. Here's nozzle. So the conservation of mass relations can be simplified even further when fluid is incompressible. Remember? Which is usually the case for liquids. Usually, but it's by and large what you use, especially when you're first starting off calculating these. So you have, and so here we have this 2 kilograms mass rate per second going in and coming out, but you don't have the same for volume, and that's because there's no such thing as a conservation of volume principle. However, for steady flow of liquids, the volume flow rates as well as the mass flow rates remain constant since liquids are essentially incompressible substances. And then here, just a note again, during a steady flow process, volume rates are not necessarily conserved, although mass flow rates are. So let's move on to mechanical energy. So this is a form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device, such as an ideal turbine. And so just a note, anytime, again, that you see ideal, this means the best case scenario, the most efficient, negating any kind of friction, that doesn't exist. It's the best ideal scenario, which means that it's never logistically possible to reach this, but this is the benchmark that we strive to. And when we're talking about mechanical work, energy is transferred through heat or work. And so in this, when we're talking about mechanical energy, it's talking about the form of energy that we can transfer through work. And we do that by using a device. So the device does work, right? Because you can't create any sort of energy or work through just a device sitting there or just spontaneous, right? So here is the mechanical energy here. And then this is mechanical energy is equal to flow energy plus kinetic energy plus potential energy. And so this is the energy change, so the change of energy, mechanical. And then here, in the absence, so the mechanical energy of a fluid does not change during flow if its pressure, density, velocity, and elevation remain constant, right? So if there's no pressure and no velocity and no change in density and no change in elevation, so it's all the same, it's all remaining constant, then the mechanical energy does not change. In the absence of any irreversible losses, the mechanical energy change represents the mechanical work supplied to the fluid. So the change in energy is greater than 0, or extracted from the fluid is the change in energy is less than 0. Okay, here, mechanical energy is a useful concept for flows that do not involve significant heat transfer or energy conversion, such as the flow of gas to an underground tanker car, because gasoline must stay at a relatively low temperature. Here you have a turbine and a generator, what is powering those. And here you have this flow from point A. So point A, right here, and then we are going down into a turbine and coming out, and here is our surface area. And then the difference here in height, right? And so here you have 2, which is the inlet going into the turbine. And then you have 3, which is the exit out of the turbine, and then 4. And so here you see you have pressures at 1, pressure through to pressure 4, velocities at 1, velocities at 4, 2, 3, things like that. So for each point at which you're changing. Okay. And so here you have A, and that is the change in water surface elevation from the upstream to the downstream reservoir, or B, a close-up of the drop in water pressure from just the upstream to the downstream of the turbine. So there's 2 different versions. Or not 2 different versions, they're happening simultaneously, but 2 different ways that you can look at it. You can kind of keep peeling back those layers, right? So here, the available mechanical energy of water at the bottom of the container is equal to the available mechanical energy at any depth, including the free surface container. So see here and here. Okay, so shaft work, the transfer of mechanical energy is usually accomplished by a rotating shaft, and thus mechanical work is often referred to as shaft work. So these are used interchangeably. And what this shaft is, so here's a little turbine, and it's on the end of a shaft. And then let's say on the shaft you have like a little, maybe a chain, or you have a cog, something like that, that's turning something else, right? And so you have a flow coming in that's spinning this around, that's making this shaft work, right? So you have the flow that is creating this mechanical work using a device for this turbine, and then that is turning this crank and this shaft, and then that shaft could be turning like, a bicycle chain or something similar, and then that could be doing something else, like, transferring all that work, that energy. A pump or a fan receives shaft work, usually from an electric motor, and transfers it to the fluid as mechanical energy, obviously reduced by the friction losses. And then a turbine converts the mechanical energy of a fluid to shaft work. And then wherever we have works and rates of work and things like that, we have mechanical efficiency, because we want to know how efficient something is. That's denoted by this N, so mechanical efficiency. And so that's the energy output over the energy input. Oh, and here, the reason it's 1 less, so this is loss over N, and that's because at 1, it's 100%. The effectiveness of the conversion process between the mechanical work supplied or extracted and the mechanical energy of the fluid is expressed by the pump efficiency and turbine efficiency. So we just have the efficiency of a pump and the efficiency of a turbine. And then here you can see these flows coming in from one, and then they all exit pretty uniformly, and we have a mass right here as well. And this is denoting the fan. And so here, the mechanical efficiency of a fan is the ratio of the kinetic energy of air at the exit to the mechanical power input. So it's just out over in. And then this just gives you an idea of just plugging in numbers really to get to this. So we have the same thing for motor efficiency here, generator efficiency, pump motor overall efficiency, and then turbine generator overall efficiency. So you can combine those devices. And here's a schematic of it, the efficiency of the turbine generator, right? So you have this turbine, right? So you have an efficiency going in and an efficiency going out, and then that is turning a shaft. So you have some shaft work going on, and then that's getting into a generator producing for rate of workout. The efficiencies defined range between 0 and 100%, of course, because it's a ratio. So you have 0%, which is here corresponds to the conversion of the entire mechanical or electrical work to thermal energy, and the device in this case functions like a resistance heater. So there's no conversion going on, none of that mechanical or electrical input to thermal energy, right? Because it's a resistance heater. So you don't, this right here, this thermal energy is the key for this resistance heater. And then 100% corresponds to the case of the perfect conversion with no friction. Those are these ideal cases. Obviously, we don't ever get there. And then the systems that involve only mechanical forms of energy and its transfer as shaft work is a conversion of energy like this. Just the in minus out equals a change of system plus the loss. And then the mechanical energy loss is the conversion of mechanical energy to thermal energy due to the irreversibilities as friction. So this is just detailing out again why we're not able to have a 100% efficient item, or why we're not able to get to those ideal cases. And it's because of the presence of these irreversibilities. So we can't reverse them. We can't extract the data out of it like friction. So the Bernoulli equation is an approximate relationship between pressure, velocity, and elevation. And it is valid in regions of steady incompressible flow where net friction forces are negligible. Okay, and despite its simplicity, it has proven to be a very powerful tool in fluid mechanics. The Bernoulli approximation is typically useful in flow regions outside of boundary layers and wakes, where the fluid motion is governed by the combined effects of the pressure and gravity forces. So you see, this is where it is valid, but when we start getting into the wakes, and the forces that are sticking to this, whatever this is, it's not valid. And the Bernoulli equation is an approximate equation that is valid only in inviscid regions of flow where net viscous forces are negligibly small compared to inertial, gravitational, or pressure forces. Such regions occur outside the boundary layers and wakes. So in a two-dimensional flow, the acceleration can be decomposed into two components. You can have a streamwise acceleration, and so that's AS, and then a normal acceleration, which is AN, and then here is the direction normal to the streamline here, and then this streamwise acceleration is along the streamline. Here's the formulas that correspond here. Acceleration in steady flow is due to the change of velocity with position. Okay. And then during steady flow, a fluid may not accelerate in time at a fixed point, but it may accelerate in space. Okay, so not over time, because we can have a steady flow. So it's the same amount, and it may not change here, but it may change in the space. And we know that because the particles increase as it exits the right side of this nozzle. Okay, and here just a little note for particles that move along a straight path, AN, so normal acceleration is 0. Since the radius of the curvature is infinite, and thus there is no change in direction. The Bernoulli equation results from a force balance along the streamline. And we'll talk and have some more visuals to help kind of solidify this Bernoulli equation. Here's all the equations. Here's the steady flow in a streamline. And this is the integrand there. Steady incompressible flows, we have these. And then the Bernoulli equation between 2 points on the same streamline is here. And then here's a note: the sum of the kinetic, potential, and flow energies of a fluid particle is constant along a streamline during steady flow when compressibility and frictional effects are negligible. So steady flow along a streamline, this is general, and then incompressible flow. And then this is some more information about the Bernoulli equation, which we're not going to go too into in this, since I have a video that's dedicated just to the Bernoulli equation. But it can be viewed as the conservation of mechanical energy principle. And it does not involve any conversion of mechanical energy and thermal energy to each other, and thus the mechanical energy and thermal energy are conserved. The Bernoulli equation states that during steady incompressible flow with negligible friction, the various forms of mechanical energy are converted to each other, but their sum remains the same. So that's that conservation we see here. And here, there's no dissipation of mechanical energy during flows. And then the Bernoulli equation is commonly used in practice, since a variety of practical fluid flow problems can be analyzed to reasonably accuracy with it. We see this a lot in just nature. We see the effects of the Bernoulli equation. And where we have forces and all of these equations, we're of course going to try and balance it. So we have a force balance across streamlines. So force balance in the direction of N normal to the streamline yields the following relation applicable across the streamlines for steady incompressible flows. So this is for steady incompressible flows. That's when you can use this. And it is normal to the streamline here. And then for the flow along a straight line, so R to infinity, and this equation reduces to here and then here, which is an expression of the variation of hydrostatic pressure with vertical distance for a stationary fluid body. And so here, pressure decreases towards the center of the curvature when streamlines are curved A, right here. So you see these streamlines are curved. But the variation of pressure with elevation in steady incompressible flows along a straight line B is the same as in a stationary fluid. So the curvature is what is key here. Unsteady compressible flows, the Bernoulli equation for unsteady incompressible flows is here. And the static, dynamic, and stagnation pressures. So the kinetic and potential energies of the fluid can be converted to flow energy and vice versa during flow, causing the pressure to change. Multiplying the Bernoulli equation by the density gives this, where P is the static pressure. It does not incorporate any dynamic effects because by name it's static pressure, unchanging, unmoving. It represents the actual thermodynamic pressure of the fluid. This is the same as the pressure used in thermodynamics and property tables. So if you have taken or are going to take thermodynamics, you are very familiar or going to be very familiar with the property tables. So this is where you would get that stagnation pressure or static pressure. Here's the dynamic pressure. So this portion here. Okay, so let's just draw a little things here. And it represents the pressure rise when the fluid in motion is brought to a stop isentropically. Okay, and then this last part here, rho GZ, is the hydrostatic pressure. And it is not pressure in a real sense, like you would equate a real pressure to, since its value depends on a reference level selected. So it's more like the pressure within the system that you're looking at, right? That reference level. It accounts for the elevation effects, fluid weight on pressure, and then be careful of the signage. Unlike hydrostatic pressure, which is rho GH, with increase with fluid depth H, the hydrostatic pressure term decreases with the fluid depth. Okay, so here, see, this is something key for your signage. The hydrostatic pressure term rho GZ decreases with fluid depth, and then rho GH increases with fluid depth. Total pressure is just the sum of our static, dynamic, and hydrostatic pressures. Therefore, the Bernoulli equation states that the total pressure along a streamline is constant because it's accounting for all of them, regardless of the state. So here's our stagnation pressure here. The sum of the static and dynamic pressures. So both of those is the stagnation pressure. It represents the pressure at a point where the fluid is brought to a complete stop isentropically. So here is that stagnation pressure hole and then static pressure holes. And so the difference between the static pressure hole and then the stagnation pressure holes is the inclusion of this dynamic pressure. Okay, and so close up of a pitot static probe showing the stagnation pressure hole and 2 of the 5 static circumferential holes. So there's one right here, whoop, probably one right here, and then one right here on the other side. Okay, and then here the static, dynamic, and stagnation pressure measured in a piezometer tube. So here you can see the piezometer, and this is the stagnation point, and then you have the pitot tube, and then P stagnation, and then pressure, and then you can use this formula as well. So careless drilling of static pressure tap may result in an erroneous reading of the static pressure head. So of course you need to be purposeful about it, not careless. Streak lines produced by colored fluid introduced upstream in an airfoil, since the flow is steady, and streak lines are the same as streamline and path lines. So remember, if the flow is steady, these are the same. They're all equal. And the stagnation streamline is marked right here. So now we are kind of peeling back the layers of the individual streamlines, the individual ones. So limitations on the use of the Bernoulli equation. We are only applicable to steady flow. So if you have an unsteady flow, you're not going to be using the Bernoulli equation, right? Frictionless flow. Every flow involves some friction in the real world, no matter how small, and frictional effects may or may not be negligible. That's why the Bernoulli equation is an approximate equation. It does get us very, very close, especially when frictional effects are negligible. But we in the real world are going to experience friction no matter what. No shaft work. The Bernoulli equation is not applicable in a flow section that involves a pump, turbine, any other device, right? Mechanical device. When this device exists, the energy equation should be used instead. In compressible flow, density is taken constant in the derivation of the Bernoulli equation, and the flow is incompressible for liquids and also gases at Mach numbers less than 0.3. And then no heat transfer. The Density of the gas is inversely proportional to temperature, and thus the Bernoulli equation should not be used for flow sections that involve significant temperature change, like heating or cooling changes. One note is this is significant, right? So when you have, like we have an example of the Bernoulli equation using a bathtub. Obviously, there is, hotter water going into potentially a very cold, especially if you're in a cast iron tub. There's obviously going to be heat transfer there, but in the real world, right, we look at it as significant temperature change. So something being heated, purposefully heated, or purposefully cooled at sections. And then flow along a streamline. Strictly speaking, the Bernoulli equation is applicable along a streamline. However, when a region of the flow is irrotational and there's a negligible amount of vorticity in the flow field, the Bernoulli equation becomes applicable across streamlines as well. So it just can't be a lot, right? It can't be a ton. Okay, so here are frictional effects, right? Frictional effects, heat transfer and components that disturb the streamline structure of flow and make the Bernoulli equation invalid. And it should not be used in any of the flows shown here. So you see a heating section, like a purposeful heating section, a long, narrow tube, lots of friction, sudden expansion, a fan, because we've got a mechanical device here. We've got another a valve here, because we're not looking at a steady flow. And then within here, right, a wake and a boundary layer, because those are not uniform like up here. So here's streamlines. When the flow is irrotational, the Bernoulli equation becomes applicable between any 2 points along the flow, not just the same streamline. And that's because you can take it from here, right? You can just assume that mathematically you can look at it here. So the hydraulic grade line, HGL, and the energy grade line, EGL, it's often convenient to represent the level of mechanical energy graphically using heights to facilitate visualization of the various terms of the Bernoulli equation. Dividing each term of the Bernoulli equation by G gives this, and that's, again, along a streamline. And then you have PL rho G is the pressure head. It represents the height of the fluid column that produces the static pressure P. And then V22G is the velocity head. It represents the elevation needed for a fluid to reach the velocity during frictionless freefall. And then Z is the elevation head, and it represents the potential energy of the fluid right here. So here, to just map out the HGL, this is the dotted line. And then the EGL is the solid line, and then the difference between those two is the dynamic head. So for stationary bodies such as reservoirs or lakes, the EGL and HGL coincide with the free surface of the liquid. And that's, you can see this is varying, right? It's varying elevations. But here in a stationary body, it's going to coincide with the free surface of the liquid. EGL is always a distance above HGL, and the two curves approach each other as the velocity decreases, and they diverge as the velocity increases. In an idealized Bernoulli type flow, EGL is horizontal and its height remains constant. For open channel flow, HGL coincides with the free surface of the liquid, and EGL is a distance above the free surface. At a pipe exit, the pressure head is 0 atmospheric pressure, and thus the HGL coincides with the pipe outlet. And the mechanical energy loss due to frictional effects, which conversion to thermal energy, causes EGL and HGL to slip downward in the direction of the flow. A steep jump or drop occurs in EGL and HGL whenever mechanical energy is added or removed from the fluid. So like a pump or a turbine, it affects it. It affects the EGL and HGL significantly. And then the gauge pressure of the fluid is 0 at locations where HDL intersects the fluid. And the pressure in a flow that lies above the HDL is negative, and the pressure in the section that lies below the HDL is positive. So here again, in an idealized Bernoulli type flow, and you see this horizontal, but its height remains constant. It's not always the case for HDL when the flow velocity varies. So you have EGL up here, and then HGL, and then you have the difference here. And then this shows a pump and a turbine and the steep jump in the two. The gauge pressure here. So here is compressible flow of a gas through turbine blades is often modeled as isentropic. And the compressible form of the Bernoulli equation is reasonably approximation. So just a note, I don't know if we've specifically gone over but what isentropic is, but isentropic is having no entropy or no change in entropy is a better no. Yeah, let's do no change. No change in entropy. No change in entropy or equal entropy. Okay? And then entropy is the presence. It's how we measure irreversibilities. Like friction. So it's the ideal, if you would have something isentropic, it's going to be also associated 9 times out of 10 with an ideal version, because an ideal version of something negates all of those irreversibilities, such as friction. And the way that we do account for irreversibilities is through entropy. So here's the general energy equation. Energy in less energy out equals the change of energy. And then you have here Q is heat transfer. So this is a heat transfer rate in, and this is work. And these are both rates. Is a change of energy in the system over the change in time, because this is a rate. And remember the two ways to transport transport energy is heat or heat transfer. We'll say heat transfer for this class, which is Q, and then work, which is W. So if we have a general energy equation, we're going to have heat transfer and work. And this is heavily covered in, This is heavily covered in the first law of thermodynamics, and it's the conservation of energy principle. Energy cannot be created or destroyed during a process. It can only change forms. And so here you have potential energy and you have kinetic energy. And right now it's sitting here, and at the top of the rock, we have all of the potential energy in the world. Well, we really have 10 kilojoules, right? But we have everything that you could have. It's all stored in potential energy. And right when it starts to fall, we start converting that to kinetic energy, because just like kinematic fluid, we're looking at the motion of fluid. Kinetic energy is the motion of energy. So it starts transforming, right? Because we're not creating. Energy cannot be created. So we're not creating any energy. And as the potential energy is leaving its potential state and going into kinetic energy, we're not destroying it because it can't be created or destroyed. It's only changing forms. We are only changing forms. So here, as you can see at some change in Z, right? Some change in elevation high. We have lost, theoretically, lost 3 PE, but that has gone and transformed into KE. So you still have a total of 10, just like you still had 10 in energy, right? So here, the energy changes of a system during a process is equal to the network and heat transfer between the system and its surroundings. So remember, we talked about the system. The system is anything that we're looking at, right? System is what we are observing. And then this boundary, so that's everything in here. It's going to be brown. Brown. That's what we're looking at. And then this red dotted line, that's our boundary. Boundary. It can be real or imaginary. So it can actually be a physical box if that's what you choose, or it can be a section of a lake, right? Like that section over there, and you can make an imaginary boundary. Everything outside boundary is the surroundings. And the system is inside boundary. Right? And so here we have heat transfer in at 15 kilojoules. We have some work in through the shaft work in, right? So we have shaft work coming in, we have heat transfer coming in. Let me change that to work. Ooh. Oh, dang it. Pressing that button. All right, that is work. And then you have heat transfer out. Okay? And so therefore, when you have the total energy, you have 15 going in, you have 13 leaving, so this is all going to be Q. And then you have plus work, because those are your two types of energy, which leaves you with 18 in your system. So heat transfer, energy transfer by heat is Q. So you have thermal energy, the sensible or latent forms of internal energy. You have heat transfer as the transfer of the energy from one system to another. Very important, the direction of heat transfer is always from higher to lower. So from hot to cold, always. Okay? And so adiabatic process is a process in which there is no heat transfer. So this would be adiabatic. And then you have a heat transfer rate. It's the time rate of heat transfer. So it's just over a time, right? So this is that time period per seconds. So work is the energy transfer associated with a force acting on a distance. So if you look back here, so you have a force, you have this shaft work over a distance. And the work being done is turning this turbine. Okay? Rising piston, rotating shaft, things like that. Power is the time rate of doing work. So if you are generating power, it's because you are using a mechanical device, piston, rotating shaft, things like that, to construct energy. So that's your power. Okay? And then you have, just notes here, shaft work, pressure work, viscous work, and then other work, electric, magnetic. It's just things to, I mean, you can note those. You can note instead of other, you can do piston, right? You can do, not piston, you could do, electric. You know, whatever you really need to do. You could put piston, but any other type of work, all of those added together is the total work. So here's shaft work. It's the force, F, acting through a moment arm that generates a torque. And so you see you have this shaft work. And you see this radius here, and that is generating a force. The force acts as a distance. Here's the formula for here, and it's in kilojoules. And here you can see the engine and how that's generating work to this fan. Work done by pressure forces. So here are those forces here, and then just denote the rates on top, those dots. So here's just a note in a typical engineering problem. The control volume may contain many inlets, many outlets. Energy flows in each inlet and outlet. Energy also enters the control volume through heat transfer and shaft work. And so you can just denote the sum of these in and out. Energy analysis of steady flows. So control volume with only one inlet and one exit, but you can still have heat transfer in and shaft work in as well. And then for ideal flow, no mechanical energy loss here. And then for real flow with mechanical energy loss over here. And then you can have it on a rate as well. And here the loss of mechanical energy in a fluid flow system results in an increase in the internal energy of the fluid and thus a rise in the fluid temperature. Here is the energy equation in terms of heads. And then a depiction mechanical energy flow chart for the fluid flow system that involves a pump and a turbine. Vertical dimensions show the energy term expressed as an equivalent column height of the fluid, i.e. the head. So there are special cases in compressible flow with no mechanical work devices and negligible friction. And so here we can talk about when it's negligible, dissipation of mechanical energy and thermal, all of that to get to this equation. It gives you a lot of historical information. This is the Bernoulli equation derived earlier using Newton's second law of motion, and thus the Bernoulli equation can be thought of as a degeneration form of the energy equation. So kinetic energy correlation factor, alpha. So the correlation factor is 2.0 for fully developed laminar pipe flow, and it ranges between 1.04 and 1.11 for fully developed turbulent flows in a round pipe. And when kinetic energy correction factors are included, the energy equations for steady incompressible flows become these. The determination of kinetic energy correction factor using the actual velocity distribution and the averaged velocity at a cross-section. We're going to stop here and have a short video that kind of puts the Bernoulli's principle into everyday terms.
What will happen if we create a strong airflow between two balls suspended on threads? It seems that the flow should push the balls apart. We switch on the blower and, surprisingly, the balls get attracted by one another. They are rotating, which means the airflow is getting through between them. Why isn't it pushing them apart? Let's carry out another experiment. We attach a funnel to a hose and switch on the blower. Then we put a rubber ball into the funnel. Instead of bouncing out of the funnel, it gets sucked into it. We turn the funnel upside down, but the ball isn't falling out of it. So why does the airflow hold the ball in the funnel instead of pushing it out? A similar experiment can be conducted with running water. If we put a tennis ball next to it, the ball sticks to the water and hangs there on an inclined thread. It looks like a fast flow of gas or liquid possesses counterintuitive properties which need to be explained. To do so, let's consider water flowing through a pipe of variable cross-section. When the cross-sectional area of the pipe decreases, the speed of water flow increases. According to Newton's second law, in order to increase the speed, some force must be applied to water. Thus, the pressure in the wider part of the pipe must be higher than that in the narrower one. Therefore, when the pipe gets narrower, the pressure in it will not rise, as it may seem at first sight, but fall. This puzzling paradox is called Bernoulli's principle in honor of its discoverer, a Swiss physicist, Daniel Bernoulli. We made this narrow neck pipe from two plastic glasses. When we blow it, the air pressure at the exit will be equal to the atmospheric one. This means that inside the narrow neck it will be lower than the atmospheric one. To check this, let us insert a tube into the wall of the neck, connecting it to a pressure sensor. When we blow the pipe, the sensor shows the decrease in pressure by 5 kilopascal, which is 50 centimeters of water column. Let us put the lower end of the tube into the vessel with colored water and blow the pipe again. We can see that the water makes a 30 centimeter rise. To increase the pressure even greater, we'll connect the pipe to the blower, which provides a far higher speed of the airflow. We switch on the blower, and what we get is a perfect water sprayer. Now let us attach a plastic bottle to the pipe and switch on the blower again. That's incredible! A decrease in the internal pressure causes the bottle to be crumpled by the outer atmospheric pressure. Let us consider water flowing inside a cross-section pipe. The volume of water V enters the pipe from the left end and leaves the pipe on its right end. The difference of pressures at the ends of the pipe does mechanical work, which equals P1 minus P2 multiplied by V. When there are no losses, all this work goes to increase the kinetic energy of water. Mass is the product of volume multiplied by density. In this case, the volume decreases, so we can rewrite the formula in the following way. The value of rho v square divided by 2 is called the velocity head of a fluid. According to Bernoulli's principle, the sum of pressure and velocity head in an ideal fluid remains constant throughout the whole pipe. This equation allows to measure the speed and volume consumption of a gas or fluid flowing through the pipe. To do this, a special device is inserted into the pipe. It is called Venturi tube by the name of its inventor. A differential pressure sensor is attached to the tube. It measures the difference of pressure between the narrow and the wide sections of the pipe. The speed of flow calculation is based on this difference. Let us switch on the blower. The device shows that 12 liters of air get through the pipe every second. This means that if the section of the pipe is 3 square centimeters, the speed of air within it is 40 meters per second. Industrial Venturis look much more substantial. They can measure the consumption of gas flowing through the pipeline with minor pressure losses.